In today's lesson, you will take what you know about the properties of logarithms, as well as how to switch back and forth between exponential and logarithmic in order to solve logarithmic and exponential equations. For our first example, how would we solve this? In this situation, we have log base 710 equals log base 7x minus 2. Well, if you'll notice, we have the same base. Log base 7 equals log base 7. So if our bases are the same, then our objects need to equal each other. If we set them equal, we can see that x must be 12. And 12 minus 2 is 10, and these then are equal. So that's an easy example. What about this example? We again have the same base, but now this logarithm is being multiplied by a factor of 2. So we're not ready to solve it yet. What we need to do is use the power rule to bring this 2 back up as an exponent first. And that would give us log base 2x squared is equal to log base 225. From here, now you can see that since our bases are the same and our logarithms are isolated, we can solve for our objects. In order to solve x squared, we take the square root. The square root then gives us x is equal to plus or minus 5. We always need to check our answers, especially when we have 2, to make sure they both work. For the 5, if we plug a 5 in here, 5 squared is 25 and these equal each other. But remember what we said, if we plug in a negative 5, we have 2 times the log base 2 of negative 5. Negative 5 cannot be the object because our object cannot be negative. If you remember, when we're graphing, logarithms look something like this, with a vertical asymptote here at x equals 0. So it's not possible for us to have a negative 5. It would become undefined. So negative 5 is not a solution. And we need to look at the object before we bring the 2 back up. Let's look at another example. Think about how you could solve this one. Why don't you pause the video and see if you could solve this on your own? Well, before we can solve a logarithmic equation, we need to have a single log on one side. So here is where the product rule comes into place. We can combine these two because our logs have the same base. When we're combining addition, that goes back to multiplication. And now we're in a position where we can solve. The easiest way to solve this one is to convert it to an exponential. Here's our base 3, so we can take our base, raise it to our power, which is 4, and say that equals our object, 6 times 2x minus 1. Now all we have to do is a little bit of algebra and simplify, and we should be able to solve for x. So I raised 3 to the power of 4 and distributed the 6, and then add 6 to both sides, divide both sides by 12, and I would get 7 1/4. We need to take our answer and plug this back in and make sure this works. So in this case, I can use my combined logs since I'm really not changing what my object is. So 7 1/4 times 2 minus 1, and then multiply by 6. I get 81. So what does that mean? Well, if I write it out, what that's saying is I have log base 381 equals 4. If I raise 3 to the 4th power, do I get 81? I do. So my answer checks out. Let's look at the second example. See if you can solve this example. Remember, first you have to isolate the log before you can start to switch to exponential and simplify. When you isolated the log, hopefully you added 12 to both sides, and you ended up with 4. Log base 3 equals 4x plus 12. And then remember this 4, oops, I left off the 81. We could raise the 81 to the fourth power, and that's what we've done in the past, but that would be a very large number. So instead, let's go ahead and divide both sides by 4, which would leave us with log base 381 equal to x plus 3. Now I'm in a good place. From here, I can switch to exponential. I know that my exponent is a binomial, but that's okay. So here's what I get. And at this point, you should be thinking, well, I can get the same base because 81 is just 3 to the fourth power. And now that I have the same base, I can set my objects equal to each other and determine that x in this situation is 1. If I look at this, I can plug the 1 in and solve and see that, in fact, this works. I don't have to worry about my object being negative or 0 because my logarithm is already defined for me. Let's try a couple more examples. Let's switch it up. Let's look at an exponential example and see how we can solve this using a logarithm. If you want to, pause the video and see if you can figure this out on your own. When you switch to a logarithm, you should have switched to log base 712 equals x. And then you learned about the change of base formula in the last lesson. So to do that, we are changing the base to 10 because that's what's in our calculator. We could also write this as natural log because we have natural log in our calculator as well. So another way that we could do this is say the natural log of 12 divided by the natural log of 7. Either one of these would give us the same answer. Remember, the only reason why we're doing this is because in our calculators, if you have a TI-84, you only have log base 10 or natural log. If on the other hand you have an Inspire, you could actually enter log base 712 into your calculator and get a solution. In my calculator, when I perform this operation, I get that x is equal to 1.28. All right, let's look at a little bit more difficult example. This is a little bit tricky. What we could do is we could switch it to logarithmic, which would be the right thing to do to solve this, but there's going to be a lot of steps involved. So an easier way to think about this is just to multiply both sides by the natural log. If I do that, this is what I get. Remember, whatever I do to one side, as long as I do it to the other side, my equation still balances. And I'm doing this to make things easier. So, what can I do now? I have these powers. I'm going to bring them down using the power rule. So, an advantage to switching exponential to logarithm is that I can do that. Since my x's are here in my exponents, I want to bring them down so that I can solve for x. Now that I have this, I can use the distributive property to distribute 2 to the natural log of 4 and negative 5x to the natural log of 4. One thing to notice about this is that I didn't take 2 times 4 because the natural log of 4 is a whole complete number here, and so I can't separate this into natural log and 4. So I have to do 2 times the natural log of 4 and negative 5x times the natural log of 4. So now I have 3 terms, and my x's are not on the same side. In order to solve for x, I need to move my x's to the same side. And here we are. So now we have my x's on the same side. How do I solve for x? Hopefully you're thinking, what if I factor out an x from each of these? Then I will have isolated x away from my elements here. And now I can solve for x by dividing both sides by the natural log of 6 plus 5 times the natural log of 4. When I do that, the expression here on the right will cancel and I'll be left with x equaling 2 natural log 4 divided by natural log 6 plus 5 natural log 4, all of which I could put in my calculator and come up with a value. Now, let's look at another example that's very similar. Go ahead and try this one on your own and see how you do. For this example, you probably multiplied both sides by the natural log here as well. Now, you could have multiplied by anything. So you could have multiplied by log base 2 or log base 4. In fact, on our previous problem, one of the considerations might have been to multiply by log base 4. And I'll show you why on this example here. So what does natural log equal? If you remember, it's the same thing as log base e. Well, let me ask you this. What is log base e? What can we raise e to get e? That's what we're saying. So log base e is the same thing as 1. So what we really have here, the natural log of e is the same thing, this is to the x, is the same thing as log base e to the x. And what I can do is circle this portion here, and I know that that equals 1. If we think about the power rule, this x comes down in front, and what I really get is x times 1. So the right side here, in fact, just equals x. So see what happens when we have log base e. Those can cancel, they just equal 1, and then whatever our exponent is comes down by default. For the left side, we once again bring down our exponent, and then we can distribute, just like we did the last time. Now we need to move our x's to the same side, so I think I'll move the x to the left and negative natural log 2 to the right. At this point, I'm ready to factor out an x, just like we did last time, and I'm left with 4 natural log 2 minus 1 equals natural log 2. My final step is to divide both sides by 4 natural log 2 minus 1, and that would leave me with natural log 2 divided by 4 natural log 2 minus 1, which, if I were to put this in my calculator, I would end up with 0.391, just in case you want to try it. Something for you to think about, this property of the base and the object being the same, if we go back to the previous problem, if I had multiplied this by, say, log base 4, that would have made the left side just be 2 minus 5x. The problem is, on the right side, we would have had to do a change of base in order to solve this. So by using the natural log, I avoided that. But it's something to consider in future problems. For our last problem of the day, we can see that we have a log equal to 2. All we need to do is switch this to an exponential problem, and then we'll have a quadratic, which we know how to solve. 3 squared is 9, and then if we subtract 9 from the other side, remember to solve a quadratic, we need to set it equal to 0. So we would get 15 here. Then we can factor into x plus 5, x plus 3, solve each of these for x, and we would have one solution with negative 5 and another solution with negative 3. Of course, it's going to be important once again to verify that our solutions are correct. So let's go ahead and verify the negative 5. Negative 5 squared is 25 minus 40, 8 times negative 5, plus 24. If I put that in my calculator, I get 9. Let's try the negative 3. Negative 3 squared is 9 minus 24 plus 24. That also equals 9. So again, let's analyze what we have. We have log base 3, 9 equals 2. Does that make sense? 3 squared, does that equal 9? In fact, it does. Both of these solutions check out, and we can use them both. That concludes our lesson today on solving logarithmic and exponential equations. So hopefully some of these examples will help you as you practice on your own.